Why is it so difficult to model coash fusibility? In this talk, I will review the history of coash fusibility testing, its relationship to pyrometric cones, and how the concept of heat work can improve our understanding of coash fusibility testing. I will also discuss how to estimate the effective viscosity of partially molten coash through thermophysical modeling and the Einstein-Roscoe equation. Lastly, I will discuss possible approaches to improving the precision, repeatability, and reproducibility of ash fusibility tests. The Industrial Revolution was powered by coal and human ingenuity. Coal mines provided the fuel for steamships and locomotives, as well as the coke needed to smelt steel. Coal-fired power plants made electricity available to factories and forever transformed manufacturing. Management of coal ash has been a problem since the beginning of the Industrial Revolution. The formation of clinkers was a major problem for stoker furnaces then and remains so even now. Coal ash fusibility testing started as a way to predict the propensity of a coal to form clinkers. The coal ash fusibility test can trace its origin to pyrometric cones. The modern pyrometric cone was invented by Seeger as a way to measure heat work, or the combined effect of time and temperature during the firing of ceramics at the Royal Porcelain Factory in Berlin. In the following decades, this approach was adapted to measure coal ash fusibility by researchers in many countries. The ASTM standard for coal ash fusibility testing remains largely the same as the method that was developed and published by the U.S. Bureau of Mines in 1918. Under the ASTM standard test method, prepared coal ash is formed into a cone and heated at a constant rate under a controlled atmosphere. Critical temperatures are recorded by an observer when the cone has deformed to match geometrical criteria specified in the standard. Likewise, the end point temperature of pyrometric cones is also measured in the same way and is analogous to the softening temperature in coal ash fusibility testing. Kiln operators use pyrometric cones for consistent results between different firings. The pyrometric cone works by mechanically integrating viscoplastic strain over time. The effective viscosity of a pyrometric cone during deformation is a function of both composition and temperature. Pyrometric cones measure heat work in a kiln, not temperature. As might be expected, different heating rates for two pyrometric cones with identical composition will result in different endpoint temperatures. The repeatability of pyrometric cones under constant rate heating is around 2 degrees C. Coal ash cones and pyrometric cones share many similarities, but are also different in how they are prepared and used. Coal ash samples are more variable in their composition compared with pyrometric cones, which have defined mineral and oxide compositions. Coal ash cones also have significantly larger ranges for repeatability compared with pyrometric cones, up to 30 degrees C for the former and around 2 degrees C for the latter. For these reasons, it is useful for us to look at how viscoplastic deformation works in pyrometric cones first. Finite element modeling of heat transfer in pyrometric cones under constant rate heating shows that a stationary temperature distribution helps to explain why cone deformation begins from the tip and proceeds to the base of the cone. The difference in the stationary temperature distribution as a function of heating rate helps to explain the difference in end point temperature as a function of heating rate, around 15 degrees C on average, going from 1 degree C per minute to 2.5 degrees C per minute. In the same study, I found that it is possible to estimate the effective viscosity of pyrometric cones during deformation through thermophysical modeling and the Einstein-Roscoe equation. The results are consistent with published three-point beam bending viscometry measurements. The Einstein-Roscoe equation is commonly used in petrology, the study of rock formation, to estimate the viscosity of subliquidous magma. The intrinsic viscosity of the molten phase is adjusted by the solid volume fraction and the maximum packing fraction of the solid phases. Direct experimental measurements confirm that thermophysical modeling, along with the modified quasi-chemical model for molten oxide viscosity, give effective viscosity estimates that are consistent with high-temperature rotary viscometry data for coal ash. The next step is to apply this modeling approach to the USGS CoQoL database, which contains coal ash oxide composition data along with coal ash fusibility critical temperature values, and see if the heat work hypothesis is consistent with predicted effective viscosities. 4,726 samples, which have at least 2 critical temperature values, were selected from the CoQoL database. The empirical distribution function of the liquidus temperature follows a bimodal distribution, which is consistent with the source data. Again, thermophysical modeling was used with the Einstein-Roscoe equation to estimate the temperature at the Lyttelton softening point of the CoQoL samples. The Lyttelton softening point is considered to be the start of the working range for glass. This approach reproduces the probability density function of the CoQoL samples at their initial deformation temperatures, best described by a bimodal distribution. The same is true of the model data at constant viscosity at the upper end of the working range for glass. The effective viscosity model also predicts that the CoQoL coal ash cones are within or below the working range of glass at their AFT critical temperatures. This is important because at 10 kilopoise or lower, glass is too fluid to hold its shape due to viscous deformation. These findings are consistent with prior work by Reed and Cohen, who also measured the steady state viscosity of coal ash slags at their AFT critical temperatures. They are also comparable with prior work on the sintering of glass particles using a cylindrical sample geometry. Importantly, while strong linear positive correlations were found between AFT critical temperatures and the liquidus temperature for coal ash cones, only weak linear negative correlations were found between AFT critical temperatures and the solidus temperature. The correlation between AFT critical temperatures and coal ash liquidus temperatures is well known and widely accepted. The apparent correlation between AFT critical temperature and the critical temperature of coal ash slags, on the other hand, requires an explanation. Since coal ash fusibility tests work by melting coal ash, and critical viscosity temperatures are measured by cooling fully molten slags, there is no causal relationship between the two tests. The apparent correlation can be explained by the liquidus temperature as a third variable. In other words, just as ice cream sales are highest where the number of people wearing swimsuits is also at its peak, the correlation between the two is spurious, as neither can be the cause of the other. Hot summer weather is the third variable in this example. Since a linear relationship is present between the AFT critical temperature and liquidus temperature, it is possible to substitute the liquidus temperature for the AFT values in earlier slag critical viscosity models through simple algebra. Back to the topic of heatwork and pyrometric cones. It is useful to note that ASTM C24 uses pyrometric cones to measure how well fire clay and high alumina refractories hold up at high temperatures. In this test, results are reported as pyrometric cone equivalents, not temperature. Data from the pyrometric cone literature can explain most of the uncertainty budget in coal ash fusibility testing. Variability due to heating rate and particle size distribution are consistent with limits on repeatability and reproducibility of AFT temperatures. In summary, thermophysical modeling of the ColdQual database shows that the effective viscosity at AFT critical temperatures are too low for cones to hold their shape. Moreover, it suggests that it is better to use the liquidus temperature in modeling slag critical viscosity. Most importantly, the pyrometric cone literature provides some useful suggestions on how to improve the repeatability and reproducibility of coal ash fusibility measurements through better control and reporting of the heating rate and particle size distribution. To conclude, coal ash fusibility testing is consilient with studies on pyroplastic deformation in ceramics engineering and pyrometamorphism in petrology, true to its origins as a test for coal ash clinkering. Coal ash fusibility testing is more likely to be useful at long residence times and high temperatures. It may not be the most suitable test for coal ash melting when residence times are short. Lastly, coal ash and slag models that rely on AFT critical temperature data can attain better accuracy and precision only by reducing the uncertainty budget in the source data. This is as important now as ever, since coal ash and slag management remain vital as long as coal is burned for heat and power.